Hello there. This is a quick blog, a video blog to share with you progress I have made in one Kaggle competition to build the machine learning algorithm. And the machine learning algorithm is aims to look at studying 3D images of protein structures within the human cell. So I'm going to share my screen. So here is the competition. The main aim is to create machine learning algorithms that automatically annotate 5 classes of protein complexes within a curated real world, basically cryo-ET, which is cryogenically captured data set, tissue samples looked through electron microscope, the data set for that. So I'm going to walk the talk here. So when I read this brief here last week, and I looked at how the data is organized, it took me time to understand what the data is, but I was didn't really have a clear. I mean, I know how to approach machine learning, but like what to use, what tooling to use. There was a bit of discovery. So I started with a tool called Cursor. I know that first step is to look at the data that is shared with you. So I downloaded the data, that 9.4 GB of data that you saw over there in that structure with test train information, understood how the data is organized, and started looking at the data. So I wrote a script with the help of it, which is effectively this one. It's so the data, the way it is organized, there's raw data in there, which are ZAR files, which are effectively very compressed image data, and there is a subset which is annotated as JSON file by experts to just show like this is what the image means. So what I'm doing now, the script is going to load it up in NAPA Reviewer. So what you see is kind of, well, the blank image is what you think. But hey, hang on. If you see this is a 3D structure here, yeah, and this is kind of a tissue sample of multiple slices and look at it from different angles. What happens is that if I change it to 2D here, you will see this is actually the raw data, by the way, right? It's one of the raw data. You will see these different protein structures. This is how it looks under the electron microscope. So now you can see that some are elongated shape, there are virus-like particles, there are smaller particles, and these are the 5 classes that it will detect. Let me close this. And what you will see next is the annotation loading up. So there are the same set data slice has been annotated. So only the subset. What you see here is that someone has actually gone and annotated the data saying, if I turn the rest of them off, right? So I'm only going to keep ribosomes on. So these are ribosomes. Now, if I put 2D on, you'll see, and make it a little bit more contrasted. So I hide this view. So these are different views, right? So same image, different views. I'm keeping at this. Now you can see where are the ribosomes. If they are there, mind where they are the ribosomes, right? So now we have a subset of raw images that have been annotated. This image will need to be fed into a convolutional neural network architecture, and the model has to be trained to identify so that when it is presented with unseen data, it can correctly predict. So the next task was that. So I have a script that I can wrote with the help of AI, which is to train the model. So train model. I'm not going to run this because it took me close to 12 hours for that script to run. And the results of that run is here. So after I designed the model, made up of effectively initially one channel, which is basically, if you remember those images, the monochrome in grayscale images, all it shows is density of the color of the black and white color. And it goes through a process of trying to capture the features in that image, and it takes it through a few layers, which is the first convolutional layer, then the pooling, max pooling, and then finally the connected layer. All it is showing is that this is how much memory that was required to process that data to train the model, and it ran over 50 epochs. What is useful here is that it has consistently converged, so the loss has been reduced. That means between training and prediction, it's quite accurate. And the fact that validation loss is decreasing alongside training loss, and basically they're converging, which means that it's not overfitting the data as well. It means the model is getting better. And it's pretty good results actually in 50 iterations that it has, the loss is down to 0.2 effectively, right? There's much of information here. I can share this in the comments if you want to read through this. But what I want to show you is a few more things, which is, let's look at this particular 3 scripts. So I want to show you is, well, not train. I don't want to run the train because it's going to cause a bit of so let me just go back from here. I go to the source folder, and in source, I'm going to go to testing, and I'm going to show you how the pipeline works. Like, am I able to correctly load the information, load the data, right? Pipeline, it's just a test function, pipeline dot, yeah, just leave it at that. That's a module I'm importing. So source.testing.test pipeline. When I run it, you will, so this is just validating. There seems to be some kind of an error here. What is it? No module found, data loader. Okay, let's fix it on the composer. This is the other beauty. So if you have a problem, because I've been moving some of my files across, so there have been a bit of issues here and there, but we're going to fix it. We're going to fix it by, I notice you have the import statement, error showing it is a trained import. So to fix it, you got to do that. Okay, let's apply that in the annotated tomogram viewer. Okay, fine. Let's fix it as hit once. And then, okay, let's try to run it again. No, still an error. Okay, let's apply that in the test pipeline. Okay, and see why. And then let's run it. Oh, seems to be a bit of unseen errors. Something new. So we see path issues. Okay. Any other things recommends? No, it doesn't. Seems better this time. Yeah, it's worked. So it successfully loaded the 140 total annotations. So ribosomes, thyroglobulin, beta-galactosidase. Right. So this is from the JSON files. So where these annotations, they have loaded the JSON files, and you see that. Similarly, let's run a few other scripts here. So we tested the pipeline. Then we're not going to run the model because we already tested it. I am going to do is I'm going to go to the training module actually. Yeah, well, not really. I'm going to go to the testing, keep on the testing, and then I'm going to testing dot test load. So this is just trying to load a test file from the test directory to see, can we load the information correctly and visualize it. It's similar to the annotated script that we ran before, but let's just run it and see what happens. Similar error with the path, because I'd made some changes in my path earlier on when I was fixing the annotated testing file. So we're going to just fix it quickly on the, yeah, there we go. Oh, we've run the test pipeline. Why have you run the test pipeline? We should be running the test loading. Okay. Okay, let's test loading. Okay, test loading. Let's see. Okay, yeah. So if you remember, we saw the 3D image, right? So if you take a slice from any angle, so this is slice number 92. So if you have a 3D image, if you look at it from a particular angle, one of those angles, the slice 2D is this. And if you look from that point of view, you see all different particles. So you can look from different angles. So in this particular slice, you see a mix of particles. So you see 4 ribosomes, 2 virus-like particles, 1 beta-galactosidase, 1 beta-amylase. So all this is showing is that the system can load the data correctly, and you can visualize it. So I think it's going to show 2 of them. I'm going to close this, and this is slice number, what is it? Slice number 51 here, and that's a different basically number of particles that you see. So distribution is different. Okay, so that loads. Next one we are going to do is we're going to test the model. I will not test the model. We're going to do is no, we're going to test the model. So this is interesting because it's going to generate a confusion matrix. Yeah, the py. Well, we don't need that. So I'm going to test the model, and what you will see here is that you see a lot of activities processing. So this is what is happening. It's looking unseen data now. So the model is looking at data it has not seen before, and it's processing that in batches because I've got it's a local laptop, so I don't have so much memory on my local laptop. So I'm breaking the test data into batches, and I'm processing those batches. 31 of them should not take more than 2 minutes. So let's see that what happens. If I don't do this, I run out of memory and the system crashes. So I had to break it up into batches. This is going to generate what is called a confusion matrix, which is false positives, false negatives, true positives, but obviously in across the 5 different classes, and we'll shortly see a picture of that generated once the 31 batches are processed. We'll also get the value of the precision and the recall scores, which is what I think the competition, references. So here, for example, it does references is that the way they are going to evaluate this is based on effectively identifying a particular metric called F beta metric. So that is used to prioritize recall of a precision. Recall means it heavily penalizes missed particles, particles which are not predicted to be true. But it's more lenient on false positives. I think that thing has run properly. There we go. So you see, there we go. Against each of these particles, these are the present. They're pretty high, 0.98 to 1, as you can see. For most of it's really done well, actually. So precisions are also high. The recalls are good, and F1 scores are good. Now, in terms of accuracy, the average accuracy is 99%. The macro average is around 83%. Right, there we go. So what is this confusion matrix that I've been talking about? You'll see a file here called confusion matrix generated, which is here. There you see, right? Now, if I make it a bit bigger here, as you can see, you see it has identified correctly or 284. It's predicted 284 apoferritin particles correctly. It's all of it actually. It's not misclassified any of those. So is the case with ribosomes. So is the case of thyroglobulin, beta galactosidase, and the virus-like particles. There seems to be some 5, 6, 7 particles it has misclassified, right? And it calls them background. But there you go. It's some it classified as apoferritin, which it is probably not. Some it has classified as a ribosome. It is one each of thyroglobulin ribosome, which is not. But we kind of have a model that actually is able to perform quite well on this complex data set. To give you an indication of what this data set means, you see the raw image looks like this. This is what we were actually looking at in the image. This is basically compressed information, and the other one is the there have been a few other bits around the annotation which are more in JSON format. So this is hope this is useful as a quick download of what I have done so far. I'm working now with more specialists, my teammate who's a professor, and hopefully we'll be able to submit this what we have done in the competition. But what I'm trying to say here is that with the developments and improvements in AI, product management as a function will significantly change. Things have become very accessible. The steep learning curve has reduced, and anyone with the right mindset can design and prototype a product like what we have seen today, and then in a very short span of time work towards making a credible product that can be deployed with and refined by the specialists. So that's about it. If you want to know more, feel free to comment and reach me on LinkedIn. Thank you. Bye.